For this video, there was a slight problem with the audio, so the first 2 minutes I will narrate as a voiceover. So this is the first of 3 parts for the Math of Automated Flight Lecture 1, and what we'll be discussing is imaginary numbers. So we know that if we take the number 4 and square it, we end up with 16. And if we take minus 4 and square it, we also end up with 16. There are no numbers in the set of real numbers that we know that if you square them, that we end up with a negative number. And this is why we introduce the imaginary number j. Now, in mathematics, we usually take the letter I, but in electrical engineering, that is how we represent current. So we will take the letter j, and we know that for j, if we square it, we end up with minus 1. We haven't seen that before, but it does open up a lot of possibilities, and the first one is that if we take the square root of minus 1, it is equal to j. Now we will continue and we'll use some properties of algebra where we take the square root of a times b. We know that is equal to the square root of a times the square root of b. So not only can we take the square root of minus 1, we can, for example, also take the square root of minus 4. And the square root of minus 4 is then equal to the square root of 4 times the square root of minus 1. And the square root of 4 is, of course, 2, and the square root of minus 1 is j. So now we can take square roots of all negative numbers. Now let's see, let's take a second order equation. X squared plus 4 equals 0. Now if we only have real numbers, we know that this does not have a solution. But if we use complex numbers, it has 2 solutions, namely x is 2j and x is minus 2j. So basically any second order equation now will have solutions. In fact, we can show that if we have x squared plus bx plus c equal to 0, we would typically use the ABC formula to solve this, and we have x1 and x2 is minus b plus or minus the square root of b squared minus 4ac divided by 2a. Now we had 3 conditions that pertain to b squared plus b squared minus 4ac, and this was also called the discriminant. And if the discriminant was positive, it would have 2 real solutions. If the discriminant was 0, it would have no solutions. But now, if the discriminant is negative, we can still write out our solutions because we can now take square roots of negative numbers. So the ABC formula now works for any second order equation. I will give an example. For example, x squared plus 2x plus 2 equals 0. We use this formula, and x1 and 2 are minus b, so minus 2 plus or minus the square root of b squared, which is 4, minus 4 times 1 times 2, so that is 4 minus 8 divided by 2a. And we can simplify this. This becomes minus 2 plus or minus the square root of minus 4 divided by 2. And we already know what the square root of minus 4 is. It is 2j. And the solutions are minus 1 plus or minus j. So x1 is minus 1 plus j, and x2 is minus 1 minus j. So now we have 2 solutions to a second order equation where the discriminant is negative. But we see that we couldn't have done that with real numbers. We had to introduce this imaginary number j. And by introducing this imaginary number j, we have introduced a whole new set of numbers. Now we know that we have, we've already seen lots of different sets of numbers, and implicitly you probably all know these. We have the natural numbers, and some take 0 included and some don't, it doesn't really matter. 1, 2, 3, etc. And that's the set of natural numbers, which is denoted by letter n. We also have the whole numbers, and that is the set denoted by z, just any whole number, negative or positive. We have the set q, which is the set of all fractions where a and b are whole, and of course b is not 0, just any set of fractions with whole numbers. And then we had the set of real numbers, and that is basically any value between minus infinity to infinity. And now we've introduced this imaginary number j, which does not fit in any of these sets. Now, we see here, we have -1, which is a real number, and we have here a number which is an imaginary number. Now, the combination of a real number and an imaginary number is called a complex number, so which we usually denote by z. Z is a plus b times j, where a is a real number and b is also a real number. Together, this is called a complex number. And the set of complex numbers is denoted by c. Now, any number b times j is called an imaginary number, and if there's no j, it is called a real number. Now, this complex number has two parts. The real part of the number and the imaginary part of the number. And note that the real and imaginary numbers are only these two coefficients. So a is the real value, or the real part, the real part of z, and b is the imaginary part of z. Now, every complex number has what's called a complex conjugate. If we have z is a plus b times j, then z, the complex conjugate of z, so the complex conjugate, z with a bar above it is a minus b times j. So if z is 2 plus 3 times j, then z bar is 2 minus 3 times j. So that is the introduction to complex numbers. So now we know what a complex number is. Let's see if we can perform some operations. So let's get rid of some stuff here. So let's say we have two complex numbers, z1 and z2, where z1 is a1 plus b1 times j, and z2 is a2 plus b2 times j. Now we know we can add regular numbers, but what would be the addition of two complex numbers be? So if we have z1 plus z2, well, the result is that we add the real parts and we also add the imaginary parts together. So this will be a1 plus a2 plus b1 plus b2 times j. So nothing really special about this. If we have, for example, z1 is 1 minus 2j and z2 is equal to 3 plus 4j, and we would want to add these two, what we would do is we would take the real parts and add them, and next take the imaginary parts and add them, and what we get is z1 plus z2 is 1 plus 3 plus minus 2 plus 4 times j, which is equal to 4 plus 2j. Now we can also multiply complex numbers. So if we have our same z1 and z2, well, what is then z1 times z2? Well, that is a1 plus b1j times a2 plus b2 times j, and we multiply this in the same way we typically do. We multiply these two and multiply these two, and we end up with a1 times a2 plus a1 times b2j plus b1 times a2j plus b1 b2j squared. But we know that, that j squared is equal to minus 1, so we get a1 times a2 minus b1 times b2 plus a1 b2 plus a2 b1 times j. So the multiplication here is pretty similar to what we have seen before. As an example, we can take z1 is 3 minus 5j and z2 is 1 plus j, and we can multiply these two. z1 times z2 is equal to 3 minus 5j times 1 plus j, and I multiply this in the same way I did before and end up with 3 plus 3j minus 5j plus, minus 5 times j squared, and j squared is minus 1, so this will give me plus 5 equals 8 minus 2j. And we see that if we multiply two complex numbers, we get a complex number again. Now there's a special case. If we have, if we take a complex number and its conjugate and multiply these with each other, if we take z is a plus b times j and z bar is a minus b times j, what happens to z times the times its complex conjugate? And what we get is a minus b times j and a plus b times j, which we get a squared plus a times bj minus a bj minus b squared times j squared. Now these two cancel out and we are left with a squared plus b squared, and this result will be used a bit later. But if you multiply a complex number by its complex conjugate, you end up with the real part squared plus the imaginary part squared. Now, so we've had addition and we've had multiplication, and let's see what we get Well, let's see how to divide complex numbers. So we have Z1 is A1 plus B1 times J, and we have Z2 is A2 plus B2 times J. And what happens when we want to divide Z1 by Z2? Well, to do this, we have to perform a little trick. We multiply this fraction by 1, and we choose to write 1 by the complex conjugate of Z2 divided by the complex conjugate also of Z2. So what are we trying to achieve here? Well, Z2 is a complex number, and we do not want complex numbers in our numerator. And by multiplying Z2 by its complex conjugate, we know we get a real number, because that is the result we had. Here we have no J term, no complex, no imaginary term. So we will end up with a nice complex number without any imaginary part in the numerator. So we know what Z2 minus the complex conjugate is. That is A2 squared plus B2 squared. And here we have our two complex numbers, where we now take the complex conjugate of Z2. So that's A2 minus B2 times J. And if we multiply this all out, we get A1, A2 plus B1, B2 plus minus A1, B2 plus A2, B1 times J, and the whole thing divided by A2 squared plus B2 squared. So what we see, and we can separate this fraction out, and I will do this quickly. A1, A2 plus B1, B2 divided by A2 squared plus B2 squared plus minus A1, B2 plus A2, B1 times J over the same numerator. And we see we have a real number here, and we have a real number times J. So if we divide two complex numbers, we end up with another complex number. Okay, so we've introduced the imaginary number J. We've seen how to create a complex number by adding a real value plus another real value times J. Together that forms the real part and the imaginary part of a complex number. We've seen how to add them, we've seen how to multiply them, and we have seen how to divide them. And in the next part we will go into different forms or different ways of writing or representing a complex number.